welcome you here. I'm Persis Drell. I'm the Dean of the School of Engineering, and I'd like to thank you all for joining us here tonight. Not only do we have a full house here in NVIDIA Auditorium, but we're streaming this event to alumni, students, and friends around the world. So we are here to honor Marcian, better known as Ted Hoff, who was the architect of the first microprocessor released in 1971. And I think it's no exaggeration to say that Ted's work and all that it led to revolutionized modern life. Now, let me just say a few words about our Engineering Heroes program. It was launched in 2010, and it recognizes the achievements of Stanford engineers who have really made tremendous advances in the course of human, social, and economic progress through engineering. We have 32 heroes to date, and they really embody all that the school stands for. Innovation, entrepreneurship, leadership, and world-class teaching and research. Along with Ted, this year's inductees are Andy Akravos, a renowned chemical engineer, and software pioneers Charles Simonyi, creator of, I'm going to use this acronym, and maybe you'll all know what it is. I had to have Ted explain it to me. WYSIWYG. How many in the audience know what that is? Okay, so the truth is I'm the new Dean of Engineering, and my background is in physics. So thank you so much, Ted, for explaining that to me. And we'll be honoring Charles here on May 12th. And I'm not going to tell him that I was the only one in the room who didn't know what that was. These three newest heroes join a very distinguished group that includes Fred Terman, Vint Cerf, the founders of Yahoo and Google, and former hero Martin Hellman actually is here in the audience tonight. He got his Hero Award for his role in public key encryption. I've got that right. So welcome. Thank you for joining us. Now, unlike many award events, the only thing we ask of our honorees is to tell us how they would like to spend their time on campus. And immediately before this lecture, Ted had, I think, a really fun conversation over dinner with a small group of Stanford engineering graduate students. We selected them to be experts in areas that were dear to his heart. And he suggested tonight's talk to provide a perspective on the influence of semiconductor technology and to emphasize the importance of technology and technologists in helping the world address current challenges. So just let me tell you just a little bit about the impact microprocessor technologies had on the world and how Ted came to play such a large role in making it possible, just very briefly. I think this is a very well-educated audience, so you know microprocessors led to technologies like computing, cell phones, the internet, things that we take for granted today. But it's not just that communications and computing that have been transformed. You know, chips are everywhere now. They're in our watches, our telephones, our ATM machines, our heart monitors, barcode scanners, traffic lights, dishwashers, children's toys. They're everywhere. Ted's interest in electronics began when he was 12, and his uncle gave him a subscription to Popular Science. And from a catalog advertised in the back of the magazine, he ordered a kit for building a shortwave radio. Not long after that, he used a cathode ray tube purchased from another catalog to build an oscilloscope. And so the seeds were planted for a great career in electrical engineering. At age 16, Ted won a trip to Washington, D.C., and a $400 scholarship from the Westinghouse Science Talent Search. Later, during summers away from college at Rensselaer Polytechnic, he worked for General Railway Signal Company, where he designed 2 circuits that produced his first 2 patents. He came out west in 1955 to get his master's. I think he never left. And then his PhD in electrical engineering at Stanford, working with Professor Bernie Woodrow, who we're delighted to have in the audience tonight, I believe. Yes, great. Thank you so much for coming. It was here at Stanford that Ted first became interested in integrated circuits. 6 years after completing his PhD, he became employee number 12 at Intel. He was brought on board in 1968 by two technology legends, Bob Noyce and Gordon Moore, who together founded Intel and earlier had founded Fairchild Semiconductor, one of the foundational high-tech companies in Silicon Valley. Now, while trying to simplify chips for a calculator, Ted came up with a solution that involved a single general-purpose processor chip rather than having to require many custom-designed circuits, and he told us a little of that story over dinner. With co-inventors Federico Fagan and Stan Mazur, he created what turned out to be the revolutionary Intel 4004. The size of a fingernail, the microprocessor delivered the same computing power as the first electronic computer built in 1946, which filled an entire room. Ted has received numerous awards, the National Medal of Technology and Innovation, which he shared with Fagan and Mazur. He was named the first Intel Fellow, the highest technical position in the company. He received the 2011 IEEE RSE Wolfson James Clerk Maxwell Award and has been named to the National Inventors Hall of Fame and is a Fellow of the Computer History Museum. Tonight, we celebrate Ted as one of Stanford Engineering's heroes and honor him with this token of our admiration. Congratulations, Ted, and I'm going to turn this over to you, and we'll give you the token after your talk.
Thank you, Dean Drell, for that very kind introduction. I also want to thank all of you for coming tonight, especially my family. You got to consider, they say I talk about technology way too much at home, so I'm lucky that they would come tonight. But anyway, my wife, Judy, two of our daughters, Lisa and Jill, and 5 grandchildren, Hannah, Connor, Alex, Kyle, and Kayla, and thank all the friends who've come. Now, I've been called various things in my lifetime. Now, a few years back, Intel ran this ad. You see, I don't know if you can see, down at the bottom I got a mention, so I guess that made me a rock star, even though I didn't have the funny clothes or the long hair. But more likely than not, the term that would be applied to me was nerd or geek, something along those lines. So being called a hero has a very nice ring to it. Thank you, Stanford. Now, technology has been good for me. Even before I got that subscription to Popular Science magazine, I was interested in chemistry. And even then, it turned out, while I was working with electronics, I was still staying with the chemistry. I mentioned I built the oscilloscope. It was a very auspicious time because this was about 1949, 1950, when television was appearing on the market. And so I even ended up using that oscilloscope to fix a few TV sets, mostly for my family or for neighbors. And even then, it turned out to be useful a little bit later on. Now, when it came time to go to college, I had to make a decision. Do I go with chemistry or electronics? Now, my uncle, the one who gave me that Popular Science subscription, was a chemical engineer. And he told me that the market in the chemistry profession probably wasn't as good as that in electronics. So I figured, let me go with electronics. It seemed like a lot of fun. And so I think it was probably the right choice for me. Now, I did my undergraduate work at Rensselaer Polytechnic Institute in Troy, New York. I grew up outside of Rochester, New York. And that oscilloscope helped me get a summer job at General Railway Signal Company. And that actually led to a couple of patents. My senior year at RPI, I applied for and got a National Science Foundation Fellowship for graduate study. Now, I figured that fellowship was probably a ticket to just about any school in the country. So why not go for the best? I applied to Stanford, and they took me. Now, I arrived at Stanford in the fall. It was actually 1958. And I was immediately impressed with Stanford. RPI was not that strong in solid-state circuits, transistors, and the like. That summer job that I'd had actually had me working with transistors, and when I started it, the junction transistor was maybe only 3 years old, so it was a real opportunity. But I come to Stanford and I find out not only are they stronger, they have just added to the faculty one of the world experts, a fellow named John Mull. I rushed to take his course and sign up for it, and I think that was probably the first time where I ever had a clue as to what was going on inside those devices. But it was really, really a good course. That was also a good time to come to California. 1959 saw 3 very important patents filed. Now the first one, Jack Kilby, Texas Instruments on the integrated circuit. But his patent really didn't cover the way we make integrated circuits today. It had some elements. But 2 patents issued and filed by Fairchild employees, one by Jean Hornet, the other by Bob Noyce. The planar process is basically the way they make integrated circuits, and Bob Noyce patented the integrated circuit. So, as I mentioned, I arrived at Stanford in 1958, and the first part is the master's degree. So, the next year, got to choose a thesis topic. And having had that railway signal job, I realized that railroads had a terrible time keeping track of rolling stock, and so I raised the issue, could we possibly build a system where we would read the serial numbers off railroad cars as they went rolling by? And I was told, have we got the guy for you? Bernie Woodrow had just arrived from MIT. And his specialty was pattern recognition and adaptive systems. And we started working together, and here it is, 55 years and still working together. So anyway, I got my PhD in 1962, and it was in that area. Now, I'd like to point out a little bit something. I probably could not have afforded to go to Stanford if it hadn't been for that fellowship. It paid Stanford's tuition, which was $1,005 for a 3-quarter year. I've heard rumors to the effect it's somewhat higher today. Is that correct? It also paid a modest living allowance. So you could probably say for those 4 years I was on the dole. But since getting that PhD, I've had pretty good income. And I pay income tax on that income. So what percentage of it should I attribute to the PhD? Say half of it. Even if it's just half, I figure over the years, I have repaid that fellowship several hundred times over. So it should be pointed out, government support of education pays off, even for the government. After I got my PhD, I stayed on doing research supported by government contracts. And that was for 6 years. And then I got a telephone call. The caller introduced himself, Bob Noyce. I heard the name. In fact, I'd met him once before. There was a time when we were told we'd have some important visitors coming to the lab. And could we put on a demo? And we had a speech recognition demo we did. Bob Noyce was in that group. So was David Packard. So was Sherman Fairchild. And I believe Fred Terman was there as well. So anyway, Bob told me he was starting a new company. And would I be interested in talking to him about a possible position in the company? It was 1968 when Intel was founded. Now, the new company didn't have a place to meet. So I interviewed at Bob Noyce's home. I didn't know what his new company would be involved, but remember, he was one of the inventors of the integrated circuit. So I figured it would have something to do with integrated circuits. And so in the interview, he asked me, what did I think the next big area for integrated circuits would be? Now, there used to be a researcher who had come from Fairchild to talk to us about students that were finishing their programs in our lab. His name was Rex Rice. And when he visited to find out whether any student would be appropriate for Fairchild, I used the opportunity to find out as much as I could about what was going on in the semiconductor industry. And I had done some work both in the summer job and at Stanford with the memory technology of the day, which was magnetic cores. And it seemed to me they were the worst part of any computer project. So when Bob asked the question, I thought, how about I answered memory? And what a lucky guess it was, because that's what he and Gordon had decided their new company was going to do. So it helps to be curious about some of this stuff. So anyway, the company has started, and they developed 2 new processes, going to start the memory business, but there was some concern. The computer companies were used to using this core memory. They were pretty comfortable with it. They'd gotten the bugs out of it. So it might be a while before they'll adopt the new technology. And Intel only had $3 million in financing. So that was a potential problem as well. But anyway, in the interview, I even had to decide, or shortly after, do I leave this comfortable position at Stanford and go to this perhaps risky startup that these 2 people, they had great reputations, so hopefully they could be successful. But $3 million didn't sound like all that much, because what if they went through the money before they had a product on the market? What happens then? But I was young enough, and I figured probably worth the risk, and so I accepted the job offer and became employee number 12 at Intel. Well, anyway, because they were concerned that it might take a while for the memory market to go, and they decided to do some custom work. And one of the custom projects was for a company that sold calculators under the name Busicom. That was one of the calculator models that Busicom made. And an agreement was signed in April of 1969, and it would be for 60,000 calculator chipsets. The chipset should cost less than $50 a kit. So at the point we agreed to this, at least you might call it a tentative agreement, we did not have the specification for the chipset. It was about 2 months later, in June of 1969, when a team of 3 Japanese engineers arrived with their specifications, and I was assigned liaison duty, not design, just liaison. Help them transfer their design. Hopefully I knew enough about the company to know who they should talk to if they had a particular question. So, being a curious type, I like to learn as much as I could about what's being transferred, and the more I learned, the more concerned I became. And so I took my concerns to Bob Noyce, who I reported to at the time. There are books out that claim that's not true, but Bob is who I reported to. And Bob did what I think any astute CEO would do. I mean, if he finds out there's a problem with the potential contract, he might walk away from it, might plow ahead and risk going bankrupt, or maybe try to get it fixed. And he asked me, could I look at it and see if there was anything we could do to maybe simplify it and make this chipset more compatible with Intel's capabilities. And that led to what I call the MCS4 project or concept. It looked like it was going to be about a dozen chips and 36 to 40 lead packages, and at that time those packages were quite expensive for our technology. So for the next 2 months, sort of played with a number of ideas, and it did seem to me there were many ways that the chipset could be simplified, mostly by making the design underlying, you might say, computation engine much more primitive, very elementary, and making it much more programmable than the original had been. And finally, we had it far enough along so that as of September of 1969, we made a formal proposal. Our director of marketing wrote a letter to Japan suggesting that they should consider an alternate design to what their engineers were proposing. That led to a meeting. The management of the calculator company came to California and received two presentations, one by their engineering staff and one by myself and colleagues. And we emphasized at that time how much more versatile our design would be, to have applications well outside of calculators. And they chose to go with the Intel design. So we were committed, as roughly October 1969, to have what ultimately would be the first microprocessor. Working parts were available early in 1971. But even though we had working parts, there was no plan at that point to make them anything other than a product for this Japanese calculator company, Busicom. And Busicom was getting itself into some financial difficulties, so there might not even be a market there. But those of us on the engineering staff at Intel began to realize whenever we had a design problem, these devices would be a tremendous help. So we began to approach marketing and say, this should become a standard product for Intel. And they said, oh no, you'll offend the big computer companies. They won't like it and they'll buy memory from somebody else. But we continued to argue, and the main argument we made was it won't necessarily be competition for the bigger computer companies. It's a new market. And we look for applications that use small amounts of memory, because if we used a lot of memory, it didn't make much sense to go to a microprocessor. You'd have a better way, and we'll talk about that in a few minutes. And we found lots of potential applications, things like control of an elevator or control of a traffic light. I mean, traffic light at an intersection, you probably have 4 sensors you have to keep track of. So there turned out to be lots and lots of applications. Ultimately, that became known as embedded control. And even to this day, I think the media does not seem to be very well aware of embedded control. And I like to point out to people that I am an example of embedded control. I have a cardiac pacemaker with a microcontroller in it, in me. So, how do we get this product announced? Turned out, in the summer of 1971, there was a shakeup in marketing. A new marketing director came in, named Ed Gelbach, and he was not nearly so frightened of offering the microprocessor as an Intel product. And so, as of November of 1971, we ran this ad in Electronic News. It was actually November 15th, the day the Fall Joint Computer Conference opened in Las Vegas. Now, people have said, did you know what you had? I say, this is not a modest proclamation in this ad. Now, as I said, Intel's goal was memory. Semiconductor memory to replace magnetic cores. And in January of 1970, Intel's director of marketing and I co-authored an article, and had this graph in it, in which we're predicting the cost of semiconductor memory will be less than a penny a bit by 1972. And we figured then we'll take over from those magnetic cores. They probably couldn't do them for a penny a bit. Now stop and think about it. If you were trying to build a personal computer, let's say, on which you would like to write a letter, the letter, one typewritten page, is probably in the order of $300 or $400 worth of memory. And so if you want to write a 10-page letter and have it all in the computer, now we're talking thousands of dollars. So again, because of that reason, we were not looking for big memory applications. We're looking for little ones. Because if a company were, let's say, had a situation where they needed, let's say, $4,000 worth of memory, they could build a very high power processor for a couple of $100. Maybe they get the microprocessor for $20. So you'd have either let's say, a $4,020 computer or a $4,200 computer, the difference being that the $4,200 computer runs 20 or 30 times faster. So that's why memory didn't make sense. Big memory didn't make sense for microprocessors. And that's why we weren't looking at personal computers in those days. But let's step forward to today. You go out today and you want to buy memory for digital camera, whatever. You get more like 100 million bits of memory or more for every penny you spend. And unlike the memory, now much of it can be non-volatile. The access time is much faster. So we have these little gadgets. I mean, sometimes they worry you drop them through a crack in the floor. They're so small. And solid-state disk drives for our computers. The progress that's been made in semiconductor technology is absolutely enormous. Our first microprocessor, the 4004, had just a little over 2,000. I think the actual number was maybe 2,300. And the typical operation in it took place in about a microsecond. And one instruction would take something like 10 of those microsecond steps. Today, your microprocessor may have billions of transistors on it and runs at several thousand operations per microsecond. So that's billions of operations per second. And so a computer that would have maybe filled a whole building back in 1970 couldn't offer the kind of performance of the processor that may be in a smartphone that you can slip in your pocket. So it is amazing, the technology. Now, people may have heard of Moore's Law. Gordon Moore coined, or came up with that phrase, actually, before Intel was founded. He was still at Fairchild, predicting that integrated circuits would double in complexity every year or two. And that's been followed almost to this day. The way it's happened primarily is by making things smaller. And we may be coming toward some limits on that. So we don't know how much more progress there'll be. But look at some of the computer applications that have been made possible by all of that tremendous advances in semiconductor technology, the smartphones, digital photography, internet access, and so on. But we also have models for various processes, but I think we can probably do an awful lot more. There's also work going on today in medical research that make use of computer applications, mapping of the human genome, and using that information to tailor-make medical treatments, particularly in the case of diseases like cancers and so on. Another area would be modeling of all sorts of processes, improving our ability to model the atmosphere, weather prediction, and things of that nature. So there are an enormous number of computer applications that have been developed, but I think there's still a lot more that can be developed. Now, at the same time, we've got all of these powerful computers. In fact, it even raises some issues about how we do the design. Most of this work has been sort of evolutionary. The second microprocessor we did was almost in parallel with the 4004. It was called the 8008. Came out in early 1972. We got feedback from that, made some process changes, and that led to the 8080 microprocessor, which came out around 1974. The 8080 was probably the first processor, microprocessor, that had performance comparable to one of the larger computers, such as a mini computer. And feedback from that led to the 8088 and the 8086. And the 8088 was the basis for the IBM PC. And then there were subsequent generations, the 286, the 386, and Pentiums, each one built on the prior architecture. So you might say we've had this evolutionary process and everybody's running their stuff on this super souped up 8008. The question I would ask someone in the business today, if we were to start from scratch with this enormous technology, is the computer that we would build look anything like what we're actually building? That's a question I think needs to be asked. Now, computers can be used for a number of things, and one of the things that they end up being used for is modeling. And we have models that indicate that some of the things that we've been doing may be causing problems. And, for example, for about 200 or 300 years now, we have been conducting an experiment with this planet of ours. We have been taking carbon in various forms, which has been buried underground for many millions of years, and pulling it out of the ground and dumping it, after we burn it, dumping the products into the atmosphere. And the models that we have indicate that is a risky proposition. At the same time that we're doing this, you look at the last century, we had a population growth on this planet of about 4 times, from about 1.5 or 6 billion up to over 6 billion people. That population growth tends to lead to things like destruction of rainforests as people move in to take out and they cut down the trees. And those rainforests are one of the things that helps remove carbon dioxide from the atmosphere. So it's not only are we dumping the stuff in there, we're destroying the drain that cleans it. Not only did we have population growth, but we nearly doubled the average lifespan of a human being. At the beginning of last century, it was a little over 40 years. At the end of the century, it's nearly 80 years. So again, an enormous. In fact, it's interesting to do a bit of a calculation. The last century was actually the last century of a millennium. We switched from the 1 as the first digit of the year to 2. Suppose we were to continue that population growth for another millennium. How much land would there be on Earth for each human being? It would be less than the area of the soles of their feet. There would be nothing left on Earth except people, which also raises the problem. What else is there to eat except other people? So something has to change there. But the impact of global climate change is also of concern. If we melt the polar ice caps, that leads to a sea level increase. That reduces the amount of land we have available. And a large part of the world's population lives close to the ocean. We also see acidification of the ocean and changes in climate change which may lead to drought. So one of the questions I would like to ask is this a recipe for doom or a recipe for opportunity? In fact, going to biofuels so that any CO2 that we add to the atmosphere had been taken out previously by the growth of that fuel. In fact, along those lines, I might like to point out, it was mentioned that Washington trip 61 years ago. The project that I had was the concept, if we run out of fossil fuels, can we collect carbon dioxide, react it with hydrogen, and recreate fuels equivalent to fossil fuels? So then we'd have a closed society. I wasn't thinking much about the damage to the atmosphere, but just the fact that those resources were finite. But it seems to me this would be a reasonable area to do some research today. It is even more important as we realize the impact of that carbon dioxide. More use of solar energy and ways of getting better efficiency. And at our home, we put in a photovoltaic system. It's been one of the best financial investments I've made in quite a while. And I think if other Californians come to the same conclusion, there'll be more of these put in, and the more we put in, the lower the cost comes. Eventually, we'd like to see the day when we don't have to be pulling coal or gas out of the ground to generate electricity, but we do it that way. And as I mentioned, the synthesis of fuels. Another area, we're facing drought. May or may not be caused by what we're doing to climate change, but that may be a factor. Desalination of seawater would seem to be a real possibility. In other words, it's still looked at as a bit too expensive, but that's partly because of the energy cost. If we can find ways to generate energy at a lower cost, we very likely can reduce the cost of desalinating seawater. And we've got a lot of ocean right off our shores here, so we shouldn't have to worry about the source of water if we can do desalination. So I raise the issue, shouldn't we be doing more to promote research and entrepreneurship in these areas? And I say, spread the Stanford model. If we go look back to the days of Fred Terman, he created what I think was one of the most unique environments ever, this relationship between the university and local business to get the concepts that were developed in the university out into the marketplace. And that, I think, is one of the things, probably more than anything, that helped create this economic powerhouse that we like to refer to as Silicon Valley. So let's keep the spirit of Fred Terman alive. And one of the concerns I have with the changes and the improvements that we're making in lifespan, if we destroy this planet, let's say in the next 100 years, there may be people in this room that would be impacted, such as my grandchildren. Thank you.
Questions?
What?
You're happy to take questions?
Sure thing.
Okay, so Ted is willing to take some questions, so we are now open for some questions from the audience on either parts of the talk. Yes.
Professor Hoff, you mentioned that in the early 1960s, along with Professor Widrow, you had developed an algorithm, the LMS algorithm. That leads me to believe that you must have been using a computer in the early 1960s. Can you talk about your earliest experiences with computers?
Yes, okay. I can tell several early experiences with computers. The first one was at the summer job. The company had a computer they used for inventory, and at one point it needed to get a relay. And you could either fill out a box of cards with the specs you wanted and send it off, and a day later you'd get a response, and it may or may not be what you wanted. Or you could go to this guy in this one room who knew the entire inventory and ask him and get the answers immediately. So that didn't look good. But when I came to Stanford with Bernie Widrow, he managed to persuade the powers that be, and boy, they were hard to persuade, to let us get an IBM 1620 computer. And that's the first one I got to program. And if you think about the 4004, the target speed for it was just about equivalent to the IBM 1620, 1 decade later.
Yes.
This isn't a question, Ted, but just a reminder. In the winter of '72, you were helping Bernie with his biomedical projects lab. And I remember you bringing in, I was sitting in on it, you brought in an attaché case. And you said, I've got the equivalent of a 1620 computer in here to the students, the graduate students. And that was really profound.
I might point out, the 1620, we had it on a special discount, so we got it at a very favorable price. And it cost $2,500 a month to have that machine. You think of the computer you get today and you pay a certain amount once and then you've got it.
Yes.
You mentioned that most machines today are an evolutionary child of the 8008. And you also phrased the question, if we had the semiconductor technology we have today, and we didn't start with the 8008, what kind of machine architecture would we build? Do you have any answers yourself to that question, or speculations to that question?
There are a number of questions along that line. Like, one of the issues, I say, with the way memory is today, the availability of flash memory, why do we need what we call an operating system? I look at, what's an operating system do for us? Well, there's resource allocation. Well, we put multiple processors on one chip these days. Why not just commit one of them to do resource allocation and not even bother the rest of the system with those details? Let any application send a request and say, I need this, and the thing will decide if you got the priority to get it or not. The other part is to make the interface what you want it to look like. Well, why don't we design it the right way in the first place? And I'm old enough to remember when you turned on a radio, you had to wait several minutes for the filaments in the tubes to warm up. There's still an awful lot of computers out there that you turn them on and you have to wait a minute for something to be loaded. It's like, why doesn't, in fact, when the transistor radio first appeared, one of the big selling points, instant on. Just turn it on and it was playing. Why aren't all computers that way today?
Other questions? Yes.
One of the most ancient battles that you helped to create was the eternal war between the hardware guys and the software guys. Within your own team that was designing the 4004, what was their background? Were they coming at the architecture and the design mostly from the standpoint of, well, let's figure out what's going to be convenient to program, or let's figure out how we do it with the fewest transistors? And how did you balance those in the first round of the eternal?
Yeah, I don't know if other people could hear the question, but sort of the battle between hardware and software decisions. Well, first of all, an awful lot of the 4004 was just me those 2 months between June and September of 1969. And having done extensive programming on an IBM 1620 and then later an IBM 1130, and I'd started playing around with a PDP-8 computer at Intel for another application, it seemed to me that as I was trying to solve the calculator problem and coming up with a little computing engine, I was programming it at the same time. So that pretty much avoided what you might call a conflict, because I would design the thing in such a way that it was easy for me to program. So later on, those decisions may have been different. When we did the 8008, the design for that device, the instruction set, so it came from an outside source. However, the instruction set had been chosen in a way that looked like it was meant to be implemented with a relatively simple architecture. And based on the experience we had and the design that we had already been doing for the 4004, it looked very reasonable to suggest they do that as a single chip. And so that's how that happened. I might point out later on, the fellow who came to Intel was asking for a memory chip. And it was actually Stan Mazer, who worked with me, was talking to the fellow and said, you know, have you considered doing that whole processor as one chip, not just the memory chip? And as Stan liked to say, he nearly fell off his chair. But anyway, later on he would go to say he brought the idea for the microprocessor to Intel. Lots of claimants along those lines. But we had already launched the 4004 at the time he arrived. But that, I think the issue of difficulty of programming probably becomes more important as you get to the more advanced architectures. And that's a case where I'm not sure that it's really been answered now. Some of these machines are pretty complicated, and even within the architecture of the machine, the operations that are going on take a lot of work. There's lots of things like conditional execution. In other words, you may pull several instructions at once and try to execute them all, and then you realize halfway through, wait, I shouldn't have done that one because it needs the result of this other one, so you back up. All sorts of stuff like that that makes the design of these things just incredibly complex. Yeah.
Did your first silicon have any bugs?
First silicon works. Yes. The first 4004s that came out were reported there didn't seem to be working at all, and it was mentioned Federico Fagin was the one doing the testing on those. He was the one who laid them out. And he said he was really, really discouraged. And then he looked at the chip under the microscope, and they had missed one processing step in making the chip. So that's why it was totally dead. So they ran another run, and these pretty well worked as spec. So
Yes, in the back.
Yeah, do you think that advances in neuroscience will affect computer architecture over the next decade or two?
in neural science?
Do you think advances in neurosciences will affect computer architecture over the next decade or two?
You know, I'm probably not the one to talk to. You probably should ask Bernie Woodrow over here. He's the expert in that field and can probably tell you where it's going. There were some areas that looked to me to be very interesting, but I haven't tracked where the research is going. Like, it was back, I think, in the mid or late 80s that the defense agency DARPA sponsored a study of the current state of research into, neural net simulation and other work in that field. And some of it even included studying the organisms' behavior and learning phenomena within living organisms and things of that nature. That looked to me like a really interesting area for research, but I haven't stayed in touch with it to see, if they really learned anything and find anything that can then be adapted into the design of equipment that we might actually build. But that I probably should pass that one to Bernie.
Do you want to try to answer it, or no? Okay.
It's imponderable. It's a work in progress.
Work in progress. Okay. Yes.
What do you think can be achieved with artificial intelligence, and what limits may exist?
What do you think can be achieved with artificial intelligence, and what limits may exist?
Well, one of the big disappointments to me is all of this progress that's been made in computers. And yet, if you want to make a computer, do your bidding, you pretty much have to learn one of its languages. They don't understand human natural language. And it would seem to me that's an area that I'd like to see more research done. In other words, so that the computer will become almost more like a companion. In other words, and not something that you have to learn Java or C or C++ or something like that. And but that's one area that I think could be useful. There's another aspect that there was work going on some years back, and again, I haven't followed it that closely to see whether it's changed, but it was sort of like artificial intelligence based on sets of rules. And the typical experiment would involve, let's say, maybe 100 or 1,000 rules. And I would argue that if the average human being has a vocabulary that's probably more like 20,000 to 50,000 words, and even each of those words may have multiple meanings, that if we do rule-based processing as a human being, My guess is we have to have more like 1 million or more rules to handle all the situations. And they used to say if you were learning a foreign language, unless you reached a threshold of somewhere around 5,000 words, you would be considered incompetent in that language. There's sort of like some magic numbers you have to reach before you're actually considered competent. So before one of these artificial intelligence rule-based machines was going to be, I think it's probably going to have upwards of 1 million rules, and that's going to take a while to program.
We have time for one last question here.
First of all, I want to thank you for this wonderful story and the talk. I've been a student for many years of the history of the microprocessor, so really exciting to meet you. I wanted to see what your thoughts are when it comes to quantum computers and the quantum processors. Thank you.
What a terrific last question.
Okay, well, there's a couple of things. I haven't done that much studying of it, but first of all, consider that we have been doing shrinking of integrated circuits. You might say it started around 1974. There was a researcher at IBM and some of his colleagues published an article proposing that they make the circuit smaller. At the time he did that, the typical feature size was called 5 microns. A micron is what, a 25,000th of an inch. So 5,000th of an inch was the resolution. That's in nanometers, that's 5,000 nanometers. He was proposing going to 1,000 nanometers. And the idea being, it's a printing process. You're printing the circuit on a piece of silicon. Make it 1/5 the linear dimension, that's 1/25 of the area. You get 25 times as many circuits on that piece of silicon. And it turns out they run 5 times faster. So you're getting like 125 times the bang for buck. Well, that's the game that's been played now since 1974. We're now in the 10 to 20 nanometer range, about a 500 to 1 reduction. People are talking about going maybe to 7. But the spacing of silicon atoms is about 1/5 of a nanometer. And the behavior of a transistor is determined primarily by impurities embedded within the silicon. So you get too few silicon atoms, even fewer impurity atoms, and you start to run into things where they're not behaving the way you expect. So that's a limit, and we've had this relatively smooth, shrinking process. If we try to go to an entirely new methodology, let's say quantum computing, there's 2 parts of it that concern me. One is it's like a whole new start from scratch process. So it's not likely to happen as neatly as the next shrink does. So that's one of the problems. And the other thing is there are some behaviors in quantum systems where the very act of reading it disturbs it. And in some cases in a rather unpredictable way. So it's even worse than a core memory where the act of reading it always destroyed the information.
Okay, well, I want to thank you very much. We have a small gift for you as a token of our appreciation, which is a plaque to recognize you as our hero. And thank you very much. There we go. And thank you for being engineering's hero. I think the audience really appreciates it. And thank you all for joining us.